example actually will illustrate how this two-step process works in detail in a very nice way. So we're showing how you can get the electric field in an alternative way through the concept of potential by first getting the potential due to a certain charge distribution, and then when you know the potential, you can get the electric field using this relation. So many of the problems in the textbooks, they focus on getting this part on its own, and this would be a certain problem to get the potential due to a charge distribution. And also they have other problems that get the electric field from the potential, but very often they don't combine both in the same problem. So combining both in the same problem is very nice, so you can see how the whole picture works in a nice way. This is the problem we have. We have a point charge Q located at this position, a charge minus Q located at this position. They're both equidistant from the origin on the x-axis. And this is a point P in space. And we've done this problem before using Coulomb's law. Now we want to solve the same problem, but using the concept of potential. So the first question we have, how would you get EY at point P using the concept of potential? How would you get the Y component of the electric field at point P? Think about it for a little bit and then continue. Well, first let's get the potential at point P and see what that is. So the potential at any point, when you have many charges, in this case you have two charges, is the potential due to charge 1, Q1, plus the potential due to charge 2. So the potential due to charge Q1 at point P is KQ over R. And the potential due to charge 2 is KQ2 over R. Q1 is just Q, Q2 is just minus Q. So you put those in and you put the distances to be R. Both distances are the same to be R. So you get this result. So you get 0. So the potential is 0 at point P. And it doesn't matter where point P is on the y-axis, you'll always get 0. As long as you're on the y-axis, the distance between the charge 1 and point P and charge 2 and point P will always be the same. And since the charges are equal and opposite, whenever you add these two terms, you're always going to get 0. So the potential everywhere on the y-axis is 0. So how does that help you get the electric field, the Y component of the electric field at point P? You know that the Y component of the electric field is minus partial V by partial Y. So the question is, how does the potential change when you move in the Y direction? Showed just now that there's no change in the potential when you move in the Y direction because the potential is 0 everywhere on the Y-axis. So that means that EY is 0. So do you see how the concept of potential, you can derive the electric field in a very simple and nice way. How did we prove that EY was 0 using the concept of Coulomb's law, if you go back to that problem we did before? Well, we got the electric field due to charge 1, we got the electric field due to charge 2, and you added them. When you added those electric fields, the Y components cancelled and the X components added. So this is the way we found that EY was 0 before in the concept of Coulomb's law. But now, in the concept of potential, we have an alternative way to get EY. Okay, this is very nice for EY, but what about EX? How could you find the X component of the electric field at point P using the concept of potential? This is going to be the topic of the next video.